In a perfect world, all problems where we use the normal distribution to approximate the binomial begin with use the normal distribution to approximate the binomial. We don't live in that world. In an almost perfect world, all problems where we use the normal distribution to approximate the binomial begin with let x be the number of successes over n independent trials of a random experiment with success probability p. We don't live in that world either. We are more likely to get a problem like this. The force required to break a cable is normally distributed with mean and standard deviation. Find the probability that at least 349 out of 400 will not break under a force of 12,400. So we see that this is a binomial probability with n equals 400 trials, and we want at least 349. We want x greater than or equal to 349 successes. But what's the success probability p? Since the cable isn't supposed to break under a force of 12,400, then we want the force y required to break the cable to be greater than 12,400. But the force required to break a cable is normally distributed, and so we need that probability. Since y is normally distributed, we can find its z-score. And then compute the probability. Now, our probability we're actually interested in is a binomial probability with n equals 400, and the probability of success. And so we can approximate that using a normal distribution with the same mean and standard deviation. So we find the mean of the binomial, which will be, and the standard deviation of the binomial, which will be, so the event corresponds to the number of successes being 349, 350, 351, and so on up to 400. And so the relevant interval, the numbers that round to something among these, will be and we can find the z-scores. And the second z-score is greater than 3, so we can ignore it. And so our interval is really just going to be the z-scores that are greater than negative 1.89. And we find the probability. Or consider the following problem. A student takes a test with 40 questions, and the probability a student's answer to any question is correct is 0.5 and independent of all the others. The probability that the student answers more than n questions correctly is greater than 0.1, and the probability the student answers more than n plus 1 questions correctly is less than 0.1. Let's find n. So first, this is a binomial distribution with n equals 40 trials, probability of success 0.5, and number of successes k unknown. Now remember, concrete doesn't hurt. Suppose n is 10. Then we'd want the probability of x greater than 10 to be greater than 0.1, and the probability of x greater than 11 to be less than 0.1. Now, note that finding either of these probabilities requires a lot of work using the binomial probability, so we'll use the normal approximation with a continuity correction. So we can model the number of correct answers x using a normal distribution with the same mean and standard deviation as the binomial. So the mean and standard deviation of the binomial will be and we'll use those as our mean and standard deviation of the normal. Now, since we're given a probability, we'll need the inverse normal distribution. So to begin with, we want the probability that z is greater than some value to be 0.1. And so we find our corresponding z value is 1.28. And recovering our x value gives us and so we can round this to n equals 24. Or can we? Well, let's think about that. Suppose n equals 24. Then more than 24 questions correct corresponds to the number of successes being 25, 26, and so on. And so our relevant interval will be, and the important thing here is 24.5 is greater than our boundary value 24.04, and so our probability will be greater than or equal to 24.5 is actually going to be less than 0.1, which we don't want. Instead, suppose n equals 23. Then more than 23 questions correct corresponds to the number of successes being 24, 25, and so on. So the relevant interval will run from 23.5 onwards, and we want to find the probability that x is greater than or equal to 23.5, which is going to be greater than 0.1, and by our previous analysis, the probability that x is greater than or equal to 24.5 would be less than 0.1 as required. And so our correct answer for n is 23.